Happy Friday morning. I'm Surendra Anabolu. I work at Broadcom, building the switch chips. I focus on instrumentation. I lead the telemetry architecture for Broadcom switches. And today I'm going to talk about ensuring the reliability of the network and how Broadcom silicon makes it possible for you to monitor the SLOs and SLAs. And just a brief background on this is SLAs and SLOs have been around for a while. And today I want to make a case like why we are building this into the silicon. It's not just a higher level software anymore. And there is a strong need and pull from the customers to be able to support this SLA monitoring in the silicon. With that, I want to get into, so let me start with, terminology. I think I'm sure like many of you are highly technical, but just I want to level set on take a minute on the level set on the terminology that I'm going to be using here. Service level agreements, SLAs, is a term that most of the people hear is often, but getting into the SLA, you need actually a couple of steps before that. Okay, so first you need to think about before offering SLA, what does the application care about? Okay, what are the kind of metrics that application is sensitive to? Okay, so and when you pick those metrics, those are called SLIs, or service level indicators. These are the metrics like, okay, what is my port rate? What are the drops? What are the latency? Am I seeing how many flows am I seeing? How many conversations are going? So that is the service level indicator. Then you move on to service level objective. The objectives are very important. These are the objectives that you need to pick carefully. That says, hey, what is the threshold or what is the level at which the service indicator should be so that the application is behaving well, customer is happy, they're seeing the expected performance out of the application. So for example, maybe you pick a target that says, okay, I want my network to be up 99% of the time or 99.99% of the time, or I want my drop rate to be something. So that is a service level objective. So you go from a metric, you're choosing a metric, which actually is an indicator of the final application. And then you go into the objective, which has a threshold that says, okay, if I meet this, then likely that my application is behaving well. The other one is that you need to note is when you think of an application, not everything is visible at the network level. Okay. So you need to pick, sometimes you get a direct indicators like packet rates. Sometimes you need to pick a indirect indicators. That could be, that indirect indicator could be something like a drop rate maybe, right? So then now we got to the service level objective that says, okay, I have my metrics and I know whether it is meeting my application objectives or not. Then you move on to the service level agreement. So service level agreement, as most of you know, is a formal contract between the provider and the consumer. And that one will specify, okay, here's my SLO. And if you don't meet these SLOs, what are the consequences going to be? So it may be, for example, maybe you need to give a discount. And typically SLAs are common whenever a customer is paying, customer is external. But for most of the providers, if the customer is internal, like maybe a cloud operator or maybe not even cloud, for an enterprise, SLOs are much more appropriate. But maybe let's say cloud operator, a service provider, where there's an external service guarantees that need to be given, then you have SLAs. Okay. So with that, let me move on to the next one. So monitoring. So I'll take some examples here. I'll take some examples here and talk about, okay, how is this going to play out, right? So we said earlier, you want a service level indicator. So I take an example here that says, you may be, commonly you may pick a port counter, like how much data am I offering, drop counters and fabric latency. So these are the important indicators of an application. So you pick them and they say, okay, here are my indicators. Then when you move on to the objectives, then you put a numbers with each one of those indicators. So for port rate, maybe you say, here is the minimum throughput that you need to hit. And drop rate cannot be more than this. And the latency has to be less than something, like you have a bound. So in this example, I have port rate of 10 gigabits and maybe drop rate of less than 0.5%, which is pretty reasonable if you want your TCP flows to behave well. And then the latency of 10 microseconds inside a data center, 10 microseconds is possible. So maybe that is the objectives. And then you move on to, once you have this one set, then you go on to the service level agreement. So that's where you talk about, if it is a cloud provider or if it is like a service provider, you talk about, hey, if I'm not able to give you a gigabit per second bandwidth that I promised you, and I'm not able to, or I'm not able to give you the latency that I offered to you consistently for so much time, maybe you get a discount or something like that. So if you look at all of this, you can see that service level objectives are very key to ensuring that your application experience is at its best. And so if you want to ensure that, and then the service level agreements also have penalties. So all of that, what this means is you must have a mechanism for monitoring the metrics in the silicon. So okay. So having said that, like let's say I'll go on to why is that becoming very important. Reliability targets for the network are getting more stringent. Okay, we are running more of the mission critical applications, and the expectations are high that network is just working. So I've been with Broadcom for a while, and I see that working with the cloud scale operators and enterprises, that the availability and the targets for the latency, everything is getting much more stringent. So earlier I was using an example of 10 microsecond latency. That's not just made up. I think there are networks with high performance networks where the latency requirements are very low. And then if you look at the availability, people are talking, used to be happy with 3.5 nines of availability. And now the new networks that are being planned, they are going towards the 4 nines of availability. So 4 nines, is like 99.99%. That seems like, yeah, okay, 99.9% you need to be up. But actually, if you translate that into actually what it means in real life, going from 99.95 to 99.99, it's a big deal because it's a simple equation, right? So you have 24 hours in a day, and then you take 365 days. That is about 8,760 hours that you have in a year. And when you say 99.95%, that is about 5 hours of downtime for your network. That is pretty hard to meet, but I think some of the operators, they have already achieved that. They're at 99.95% of downtime. Now they're planning for 99.99, which seems like a small increment. But if you go to the same math of 8,760 hours and take 99.99, that comes to be under 1 hour of downtime. To be more precise, like 53 minutes of downtime in a year. How are you going to hit that? How are you going to achieve this? And that's where the monitoring comes in, your SLO monitoring comes in. So on the right-hand side, top right-hand side, I have an example that shows, okay, it's a typical network where you have a lot of multiple paths that are going through the fabric. So, and the reliability is built in. So the network is designed to have that reliability, to provide you that 99.99%. Let's say I am monitoring everything at the end stations. And I'm saying, okay, do I have the connectivity? Is everything working well? Yeah, seems like everything is working okay. Let's say one link went down. A link going down is an extreme example, but I'm just taking that to make it very obvious. You'll still see the end applications will still be behaving right because you have a lot of alternate paths. What if the second link goes down? You may still be able to see it because the networks have 4x the paths than needed. But if you let it continue, there'll be a point where the application fails. And if you're monitoring only from the application point of view, and if you don't have this monitoring built into the network in the silicon, by the time you realize it's actually a big problem. Maybe you have a small problem that will cascade into a big problem. And by the time you realize it's down, you won't be able to meet your under 1 hour of downtime. And there will be unexpected things that happens, but you want to monitor it and detect the small problems before they cascade into a big problem. I think this example is like, it's more like, okay, you have a small fire, like in the kitchen or something. It's easy to put it out there rather than waiting until the smoke comes up on the building and then you have fire engines rushing in. Of course, you fix it, but then it's very expensive, and then your downtime is going to be very large. So with that, so I hope I made the case that why you want to proactively monitor the networks, and because of the stringent availability targets. This other angle that we see actually is that it's not just that you have lower downtime requirements. You're also requiring much more fine-grained telemetry. Why is that? Because if you look at first generation of the products, Bhaskar talked about using SNMP, and then you have seconds, tens of seconds of granularity. The kind of network loads that you see in the fabric now they're increasingly getting more and more bursty. You may have like a small request packet that comes from outside the network. And actually, if you go on, I think Google has a video somewhere that shows what happens when you do a search or something. So you have a small request packet that goes in, and that actually causes large number of requests inside the network. And they shard it across the multiple servers, and all these servers come back with results. They all have to be combined. And this creates what is popularly called as microbursts. So I kind of like put it on the chart. The blue line is showing the microburst. And what happens if you actually go look at this at 10 seconds resolution? You won't know that the microburst has happened. So you will see that, oh yeah, my port is looking good. Okay, I'm at 30% utilization. So my capacity is okay, and I'm doing fine. But are you really doing fine? Then you're having issues because your microbursts are like actually using most of the network bandwidth for short usage time. And you may actually be having packet drops that you're wondering, why am I having packet drops? And my my ports are the only utilized 30%. So you don't have very good visibility. The other thing that you find in this in the first generation of product is that there's only port level visibility. You don't have class of service. You don't have queue level visibility. Most of the silicon in the fabric supports multiple queues, but just because a port is very highly utilized doesn't mean you actually have issues. Because if you have a TCP traffic that expects to take up whatever is usable, but your high priority traffic is where you have these service level guarantees, and they are working just fine. So you do need queue level telemetry. So that's where I get to here. So then we move to offering queue level telemetry, and then you will also find that the resolution has gone up milliseconds to a few seconds of resolution. So now let's say if I take the same microburst, let's say I go look at the using averaging time of milliseconds, how does it look like? So now you have a much better view of what is going on there. So you do see that there's microburst happening. So you're better off, but you still don't see that actually the line is actually getting saturated for periods of time. And you may still have packet drops that you can. So I'm at 25%, I'm having packet drops. Is this because there's a switch is malfunctioning, or do you have policies that are not set up right? Why am I having packet drops here, right? So and knowing that exactly when you have a clear visibility of the network, then you have the confidence to rule out some of the possibilities and go and do something else. When I look at BroadView Plus that Bhaskar has been talking about, as talked about in the last section, where Broadcom silicon on the XGS, DNX, Tomahawk, Trident, and Jericho line is offering. BroadView Plus offers flow level telemetry. Flow level telemetry meaning you have visibility down to conversations. So you have for each conversation, you can figure out what is the traffic rate that's going on, and what is the latency. So you have flow level telemetry. And then the streaming wise, you can stream the data at microsecond level. Bhaskar talked about streaming telemetry, which actually significantly reduces the load on the host, and it reduces the load. And actually, from the silicon, you can stream at microseconds. And with each of these reports, you also get timestamps. When is this event observed, and when is this exported? So you get these timestamps so that you can correlate later on. And these timestamps are at nanosecond granularity. So you have timestamps that are nanosecond accurate that goes with these reports that go along. It may feel like, okay, why do you need nanoseconds? But we hear from the customers actually, there's a metadata of this timestamps can be used to correlate with other events that are happening. And also you will find that the collectors can actually calculate, once you have very accurate timestamps, what is the burst, how is the network health is. So you get all of this. And in addition to that, with the flow level telemetry, you get the 5 tuples. What are the 5 tuples that are going through the network? So you know who is using the most of the network, who is the victim, who is the aggressor, and that is a fine-grained telemetry that's necessary. And why is this necessary? Because SLOs are written for the application. You can say, okay, I have an application like an ERP application or a web cache application that requires certain bandwidth or certain latency. It is not useful to say, hey, my port, like my end-to-end latency on the average is 100 microseconds. But for what application? For what queue level? And if there is a issue with an application, Is it that particular application that got affected? Is the packet drops that I saw in the switch, are they related to this application? Are they related to some other application? So you want to be able to rule out. So you do get at application level visibility with the BroadView Plus. Okay. So with that, I'll so having talked about the fine resolution, I'll say, okay, now let's say you have SLO monitoring in action. How does it look like? So I started with talking about, okay, application is important. And sometimes you need to drill down to the flow level so that you know what is the level of guarantees and how many of the flows are exceeding this level of guarantee. So actually, I can share with you one of the interesting SLO a large customer of ours was working towards is that it is not just that, okay, this application meets this one. And to say an application is available, they would like to say, hey, 99.9% of the flows should not be experiencing more than 2% drops. So it's not just that, okay, there's no drops. There is allowance for a certain number of flows. So you do want to know if there's an effect that's going on, if someone is seeing a drops, how many of the flows are experiencing this drop. So you do need flow level. And you need to track these in the pipeline because of the rates that I mentioned earlier. So we are talking about nanoseconds and microseconds, and that is next to impossible if you do that in the software. So you want to track this, you need to do this in the pipeline. And then, okay, then the thresholds. These thresholds need to be customized for the application, or for group, or per service level that is offered. So, and once you have all of this, I put a table here, it's just more like a markup. I actually have a demo that's coming up that shows you how it actually shows up on the software side. So here I'm showing, okay, I have multiple applications that are going on, and how much is the network usage for each of these applications, what is available to members. And we even have the ability to say how many flows are going through the switch, how many unique flows are going, how many unique users are going through, and we can count them to the millions. That's not an issue. And for these applications, then we can actually show you what is the latency, what is the average latency, what is the 99.9 percentile or quintile latency, what is the top 10 latency. So you have this both the average and the quintiles. And then of course you have the packet drops that Bhaskar talked about. You can track them by the applications, right? So you have all these capabilities that's built in to the silicon. And we have CA acquisition that Broadcom made. It came with some of the very excellent tools for utilizing these capabilities that are in the silicon. So silicon provides all this, but you need some software to bring them out. So Jeremy that did the last demo did this demo as well. It's a pay card demo. It's 5 minutes. Let me show that to you, the demo that Jeremy did.
AI Ops from Broadcom, powered by next-generation silicon and telemetry, gives you a simplified service view of your critical and non-critical business applications based on many factors, but especially the user experience. Here we have an application-centric view of availability, or we can sort by other factors like alarms, users, KPIs, and predictions. So we see we have an availability issue within the fabric of our private cloud service. So let's investigate that further in context. Our service analytics summary gives operations teams easy and simplified SLA and SLO intelligent metrics like risk levels, user counts, and availability over time. We can also see alarm analytics in action, where we have 193 raw alarms automatically reduced to 2 anomalies and 2 service alarms. Our topology visualization of the service enables quick triage of healthy infrastructure, their relationships, and even the weight of how this degradation is impacting the overall service. Looking at the first of our 2 service alarms, we see an unresponsive Ethernet 32 interface. For more information, let's view the related alarms that were automatically correlated into this service alarm. We are now looking at the root cause of the service impact, automatically detected by our analytics engine, along with the associated alarms as well. Our AIOps engine intelligently understood that when Ethernet 32 went down, because of failover rules in place, traffic has now breached thresholds on Ethernet 31 on the same switch. Clicking on the Affected Metrics tab shows the machine learning algorithm used to identify the associated anomaly alarm. If we look at the anomaly detected, this is not your normal SNMP data. This is per packet data we're getting directly from next generation Broadcom silicon and telemetry. The switch and embedded silicon itself is telling us that there's congestion on Ethernet 31 now, due to an unresponsive interface 32. We can compare metrics for even further validation. Not only are we seeing network congestion issues for interface 31, but as a result, we're also seeing packet drops for the same interface. This easy comparison can show how this abnormal network activity and behavior is obviously related to our service degradation. To realize the power of real-time chip-level access to network performance data and understand the effect this has on our service traversing this infrastructure, we can dive deep into AIOps deep packet and flow analytics for fine-grained network visibility. This is a very powerful dashboard for operations because it allows easy access to understand the applications affected by network congestion and the culprit behind our degradation. Instantly, we see where the congestion is, related packet drops, and most importantly, because of Broadcom's Inband flow analyzer, we get flow information at packet-level granularity to understand the application impact. Let's look at the flow affected within this queue. Network administrators can set application-level performance targets such as max end-to-end fabric latency with granular drill downs to the application level or flow level down to the packet level. Our topology diagram on this dashboard shows packet path tracing and shows us the path this specific flow took over our switch fabric, as well as our culprit switch again. Per packet latency is where we can see where the latency of flow 108 as it traverses the network. As it moves from switch to switch, we easily see it spending more time at our 10.27.37.228 switch. Each one of these bars is a per packet view of flow 108 in nanoseconds, the most granular visibility and network performance in the industry. Because we timestamp each packet as it crosses our silicon, each bar here shows the time this packet spent at each hop. This is gold to network engineers and architects and helps them immediately pinpoint congestion affecting the application experience, along with proactive SLO and SLA monitoring. The Broadcom solution detects problems before they happen. Slow degradation and small failures are caught early before they cascade into larger revenue-impacting outages. For even further visibility, we enable Layer 2 topology visualizations of your leaf and spine architecture and the direction of traffic depending on the application flow. AIOps from Broadcom, powered by industry-leading networking silicon and advanced telemetry features such as Inband flow analyzer, enables the most granular visibility into network degradation impacting the application experience, as well as proactive monitoring for SLA compliance. The solution reduces root cause analysis for isolating application latency issues from weeks or days to just minutes or seconds. Driven by BroadView plus telemetry directly exported by networking silicon, Broadcom's solution delivers the highest scale with best-in-class TCO.
Okay, that was Jeremy going through the AIOps. And I want to show you actually what is happening under the hood. Because, okay, there's all these graphs and charts, and then earlier I was talking about like how all this final resolution is important. So I want to show you like what is happening under the hood. And actually one thing that to keep in mind is like, I think Jeremy was talking about how we all these things are packet level, and then we are doing this at final resolutions and everything. And it takes a lot actually to do it in the switch silicon. I've been doing the switch silicon for a while, and then like say for example, like this is one of our Trident series silicon. There are like 20 plus billion transistors that are built into this. 20 plus billion transistors, and that's made possible by the architecture and the advanced technologies that are coming here. And I want to show you actually what are these 20 plus billion transistors are doing underneath. Of course, the switch, the primary function of the forwarding is going on, but in addition, we have built an instrumentation plane. This instrumentation plane works orthogonal to the forwarding plane and gets you all these features while the forwarding plane is doing its job. So Jeremy has talked about how this is per packet. I mean, some of you may be wondering, how can you do this per packet? How can you show me? Because there's each of these switch chips, as you know, Tomahawk can go at 10 plus terabits per second. Even Tridents can go at Tomahawk, Trident, Jericho devices. They go at terabits per second. And we are talking about getting the flow level data, getting the nanosecond data, and getting packet level data. How is that all possible? And there are a lot of metrics that you could measure. So there is like rate, drops, latency, and all of them you can measure. So what happens, what you'll find is that once you get to this level, when you want fine resolution and you want flow level, and also keep in mind that over the years, the capacity or the size of the data center is also growing. If the size of the data center has gone 2x, 4x, the level of resolution has gone 10x, 100x. So when you do that, there's so much amount of data. There's a lot of data. You can easily have a terabyte of data coming for just telemetry alone if you just do it in the plain old methods. So what we have in the silicon, that what we built is, we want to get you the data that matters, to translate this data into information. So how does it happen? So, okay, we have all these packets going through, and then we are measuring latency, drops, jitter, various counts of this, like flows, number of unique flows. We are measuring all of that. And the first thing we do is, like, remember that we talked about the SLIs and SLO. So SLI is your metrics that you're looking at, and SLO is with the objective. Here, what we do is we say, okay, my objective is that the latency is no more than this. My objective is that packets are not getting dropped, or at least the drops are less than something. So first thing we do in the silicon is the threshold processing. So by threshold processing, like software can come and configure, here are the thresholds for the various different applications. These are all again per application. Here are the threshold for various different applications, and this is what you monitor for me. Okay, so the threshold processing happens in the silicon. And the next, okay, threshold processing does reduce significantly. See, it's not that every packet is going to cross the threshold. It's probably maybe 1 in 1,000, 1 in 10,000, 1 in 100,000 packets crossing threshold. That does a lot of filtering. But is that enough? No, not really, because even if after you do threshold processing, you still have very large amount of data. Imagine like one of the flows that is going through, and it's because of rerouting or routing around, it is experiencing excessive latency. If I want to be doing threshold processing, I'll be sending you that packet. If there are 10,000 packets in that flow, I'll keep sending you that packet saying, hey, by the way, this packet has exceeded your 50 microsecond latency target. Oh, again, this packet exceeded your 50 microsecond latency target. What we do is we have stateful engine that's built in. So what does the stateful engine do? The stateful engine can actually learn the flows automatically and look for the thresholds, look for have I notified this event before? So let's say there's a new flow that comes in and it's working fine. We're not going to do anything. Thresholds are fine. And then let's say because of something else happened in the network, there's a rerouting or something happened, your thresholds are crossed. Then we are going to send a notification saying, hey, this particular flow is seeing excessive latency. This conversation is seeing excessive latency or excessive drops. And what if the subsequent packets are also experiencing the same thing? Then we're not going to be sending every packet. We are just going to go sample 1 in 1,000 saying, yeah, this flow continues to experience excessive latency. And when actually this condition is resolved, then we can send another notification saying, hey, now everything is within the norm. What just happened, what are we doing right now is that instead of just sending you 10,000 packets in the flow that all exceeded this particular threshold, we send you very few handful of packets to say that this event happened and this event happened and you are seeing this anomaly. And then you will say that, okay, this is happening, and then say, okay, this has resolved itself. So that is what we talk about, like data that matters, are a way to convert the data into information. And then, okay, we are not done yet, actually. So even at this point, it's not something that one single server, a few collectors can process this amount of data, especially in the cloud scale customers. And a lot of this, Broadcom being the leading silicon provider, we work with large number of customers and we get the benefit of that knowledge of where the customers are heading to. And this pipeline that we built is in response to actually a few of the large customers that we have. So the final stage that we have before the data leaves is the streaming telemetry, where we actually support PubSub model that Bhaskar was talking about IPFix. IPFix is a data format. But here you can actually say, I have various data streams, and the collectors can subscribe to saying, okay, hey, I want to see the jitter information. I want to see only when this particular type of drop happens. Bhaskar told you that there are many types of drops, dozens and dozens of drops. Somebody can just subscribe and say, hey, I want to see whenever there's a TTL drop, which is usually by routing loop, caused by routing loop. Or maybe a different collector is monitoring the congestion. I want to see congestion drops. So there's multiple streams of data that is available, and it can be the collectors can subscribe to what they are interested in. I hope this makes the case why this has to happen in the silicon and why the silicon complexity is necessary, so that you can actually proactively monitor and then at a fine granularity. So,
sorry, does that mean that the silicon is keeping track of the flows for the duplication?
Yes, I think depending on the objectives. So for deduplication, silicon keeps track of the flows, and the flow doesn't not necessarily mean the 5 tuples. You can define, here's the definition of a flow. The flow could mean the destinations are. So silicon has state, and it can keep track of the state.
Okay, thank you.
Things that that is a new innovation that is added to the Broadcom silicon in XGS and DNX line, saying that we need state, and some of the operations are stateful, and that actually helps you deduplication. And actually, there's a very good question. Sometimes the question comes up as, hey, like sometimes maybe state may be so much, you may not be able to keep up with all the state that's going on. So the customers we worked with, they said, hey, we know when there's a lot of data that's coming from one particular type of event. And we can tell you saying that, okay, hey, keep track of this like a cache. You dedupe this particular categories for me, because that will be 99% of the deduplication will happen in the pipeline. And the rest of it, that the infrequent duplicate things, we'll handle it in somewhere else in the collector. That's a good question, actually.
Surendra, may I interrupt?
Yes.
Is the streaming telemetry only sent in the event of a drop, or is it streaming telemetry for every flow that is seen across the silicon?
The drop is one of the sources. Streaming telemetry can be used for various different things. It could be for latency as well. So you have multiple sources we talked about. So there's multiple, we publish multiple sources that somebody could subscribe to. So it could be drops, it could be latency, it could be any of the telemetry applications that are running on this silicon.
I'm just wondering, in the case of, I think it was many slides ago now, but there was a two-tier, or I guess single tier clause. In order for a packet to go from one server to another, it has to cross 3 switches. Does that mean all 3 switches are sending telemetry? So that means, like, for every packet that's sent, we get streaming telemetry 3 times from 3 different sources?
It is possible, depending on the deployment. If you deploy IFA, which is end-to-end technology, you could do everything at the end node, and that is actually recommended. And as you guys are all technical experts, as you have pointed out, sometimes if you do end-to-end, you do need support across. Otherwise, you'll have holes in the network, in which case you may want to do per node. But typically, we recommend that you do end-to-end. That way, you get significant compression in the amount of data. So, and also typically, the top of the rack switches tend to be lower capacity, and where you can actually get a good scale out that way. So the end nodes can actually do the streaming with the IFA, Inband flow analyzer technology, which is end-to-end.
I'm just thinking sort of, like you keep talking about cloud scale and how that scales out, right? For every flow that's seen, I guess every packet that crosses, it's sending more telemetry multiple times for every switch that that packet passes through. That's got to sort of multiply the volume of data for the collectors.
Okay. So one thing we find is that, that's where cloud scale and enterprises and service providers are slightly different. Cloud scales, they deploy these huge homogeneous systems. So they have this template, they just replicate that across the racks and class and everything. And they tend to be very homogeneous. And we find that actually cloud scales devices are homogeneous, which allows us to enable in-band technology. So typically what I find is cloud scale customers, because they are homogeneous in terms of the technology that is deployed, and they upgrade the whole thing. They're not going to go and say, hey, this switch is down, and by the way, I have this new switch that is more capable, let me replace that with this. No, they don't do that. If the switch is down, that stays there, and then maybe in the next data center that they're going to build, they'll have a new technology. So because of that, it makes it easier to deploy in-band flow analysis, which is end-to-end technology. So you actually less likely to see this every switch streaming in a cloud scale.
Thank you.
Yes. So I have a couple of more slides. I just want to explain things that you saw in the demo. So the previous slide was more about like why you need this in the silicon because of the requirements of the SLO monitoring. And here I just want to explain that, the 2 things that Jeremy has showed. One is the latency monitoring, and then also the end-to-end drop monitoring. So these 2, the demo that you saw was the in-band technology, which is basically end-to-end. And here, what I'm showing you here is, this is a very simple, of course, very simplified topology that I'm showing you. S11, S21, and S12 packets are going through. Bhaskar has showed you how the in-band technology. I think one of you had a question on where is the IFA header, the in-band technology header is added. I have in this slide that says it is after the IP header, where the IFA2 header is added, and the metadata is added after the L4 header. Okay, so because of that, if you have a switch that is in the middle that doesn't know about IFA, it can still forward by IP. But we do prefer that when you deploy end to end, everything is IFA capable, because that way you don't have any holes anywhere. And then because every packet that's going through, and at every hop you get ingress timestamp and egress timestamp, it becomes very trivial. Actually, it becomes very easy to say when the packet reaches the end, what is my latency, end-to-end latency? Did I cross a threshold? And that becomes very simple. Because IFA being end-to-end, it's very easy to process, because many customers, they care that what is my fabric latency, not just what is my switch latency, what is my fabric latency? And here's the application is expecting certain fabric latency guarantees. And so you'll be able to do monitoring for end-to-end using the IFA that way. So, and then let me go to the next slide, which is the per application packet drop monitoring. Even here, you look at it, because it's end-to-end, we can do some newer things that you cannot do per hop level. So if you want to say per application end-to-end, so if you think about it, let's say you do switch level monitoring, right? How would you know if a packet is dropped in the wire, right? Actually, our customers tell us that it's not infrequent that packets are dropped in the wire, in the cable, right? So if you just do only a switch-based analysis, it is harder to figure out that, okay, this many packets are dropped in the wire. But whereas if you do end-to-end analysis, it becomes easier to find that, okay, hey, I sent so many packets, I received so many packets are dropped. But how do we do that? It's because we have state in the chip, and using the state, we can say, I have, let's say, 100 applications that are running. For these 100 applications, I'm going to be marking the packets, let's say red and blue, right? So you mark them red and blue. And then I change this marking, let's say every 1,000 packets. In this particular example, every 4 packets, right? So if I'm changing this color every so many packets, usually we do 1,000. Let's say every 1,000 packets, I'm changing the color. On the receiving side, I should be able to see, okay, for this particular source and destination pair, because it's colored this way, this many packets are missing. So this many packets got dropped, and that is possible. You can do this across the network, or you can do this across the 2 switches that are next to each other. And by doing this, you can figure out how many packets are lost in the wire as well, not just in the switch. So that is basically 2 examples that you saw Jeremy doing demo, and I wanted to explain. And with that, I want you guys to have 2 takeaways. The first one is that the requirements, the targets for the SLOs are getting really stringent. You're going to 99.99. And it is real, actually. It's like I see customers going from 99.95 to 99.99, which is very, very stringent. And there is very fine-grained and proactive, fine-grained telemetry that's being asked, because we want to know not just that the network is congested, what application is getting affected, and what is the flow level statistics. And the last point I want to make, I hope I demonstrated, is Broadcom silicon delivers the information that matters, right? It's not just we are streaming all amounts of data, like saying that we can monitor all this. It's we filter them down to information, allowing the customers to build a high-performance telemetry platform that can scale across the cloud scale, while at the same time monitoring at very high resolution and monitoring all the packets.